asked to find the square root of something, you're actually being asked what times itself gives you the original number under the square root bar. Because actually here, there is an invisible 2 there over the square root bar. So the idea is that this right here is asking you what to the power of 2. See how that corresponds, the invisible 2 with the power of 2? What to the power of 2 will give me 25? Or you could think of it as what times itself equals 25. This right here is a pretty basic one. Hopefully you guys are thinking 5 times 5 equals 25. So in other words, the square root of 25 is equal to 5. But the idea is, of course, they're not always this simple. They're not always perfect square roots. So to review some perfect square roots, let's list them out and just make sure that we kind of know what a few of them are. Perfect square roots. Let's see, 1 is kind of trivial. 1 times 1 is 1, so I'll start with 2. 2 squared is equal to 4. 3 squared, or 3 times 3, is equal to 9. 4 squared is equal to 16. 5 times 5, we just said, is 25. 6 squared, or 6 times 6, is 36. 7 squared, that's a 49. 8 squared is 64. 9 squared, 81. 10 squared is 100. And we can go on and on with that. So that's a list of some of the perfect square roots, and of course it does go on forever. The idea is, in solving square roots, that ideally you're going to have one like the square root of 25, where you just get a perfect square root. But in math, it happens probably more frequently that you don't have the perfect ones. So we need to be equipped to handle those, and we need to be able on your test to solve those by hand. So looking at an easy one like 25, I want to introduce one method that you may find easier than just asking yourself, what is the perfect square root? If you did not know that 5 was the perfect square root of 25, an optional method, instead of just evaluating the 25, is to do something that I'm going to call the tree method. It helps you to break the number into smaller pieces so that then you can identify what's being repeated. Of course, we're talking about being repeated 2 times because we're talking about square roots. What's being repeated within this number by multiplication. So for example, if I were going to practice this method on one like 25, I would have taken the 25 and I'm going to find the prime factorization of this 25. Remember that prime numbers are numbers that are already as simple or as small as they can get. So for example, 1, 2, 3, 5. Numbers that nothing except themselves and a 1 can be divided into. They can't be broken down any further. So I'm going to take 25 and break it into its most basic pieces. In other words, I ask myself, is there a prime number I can pull out of 25? Sure, 5. 5 times what gives me 25? 5. The next thing I ask myself is, can I break this 5 up more? No, they're both primes, so I stop here. At this point, these pieces, these 2 5s, make up our 25. So 25 is equal to 5 times 5. What we're looking for, since we're looking at the square root, so for square root, we're looking for pairs of 2. So see here how we have a 5 times 5? What we would say here is, okay, so the answer, what's being times itself 2 times, is equal to 5. So again, you can evaluate these things directly if you already know the perfect square root. Or you can break them into their smallest pieces and look for repeats. And when they repeat, for every 1 time they repeat, or for every 2 times you have the number, sorry, you get 1 number that you keep, that you pull out of the square root. So it's kind of 2 ways to look at it. Let's look at it with harder problems though, because probably a lot of you did know square root of 25 is equal to 5.
Okay, so just to be clear, we have looked at the square root of 25 in two different ways. We've looked at it in the easiest, most basic way as saying, okay, we can divide this number into 5 times 5. And since that repeats, our answer is 5. And we also looked at it by treeing it out and looking at repeats. So the same idea, but two different methods to get to that same answer. Looking again at that multiplication idea, technically that's called the product rule, guys. So here at this example, square root of 72, I'm going to explore the idea of product rule more thoroughly with you. Notice that with 72, I can break that into two numbers that multiply to equal 72, 36 times 2. I can actually rewrite that then, the square root of 36 times the square root of 2. I can break it apart once I've written it with multiplication. Now, I chose 36 because I know, looking over on the left, that that is a perfect square number. That's something 6 times 6 is equal to 36. So when I broke up this 72 that we're looking at here, I did it very carefully, making sure that one of the things I broke it up into had a perfect square. So when I look at that, again, the square root of 36 is 6. I can go ahead and cancel that and write 6 in place of that part. That gives me 6, and the leftover part is square root of 2. Remember, guys, there is a multiplication attaching those two pieces, so even though I'm not showing it, technically here we have 6 times the square root of 2. Now let's look at our other method, the way that we visited the 25 a moment ago when we turned it into trees. Looking at the square root of 72, the prime factor.
Use the trees. So I'll say 72, 2 goes in there. We can see that with that 2 on the right. So 72 divided by 2 is a 36. Break the 36 down. 3 and a 12. 3 and a 4. 2 and a 2. These are the pieces that make up 72, right? So actually, I could break this up into multiplication by its primes if I wanted. So remember the other time we looked at it, we just broke it into two pieces, the biggest square root we could think of, and whatever it had to times by. In this case, though, we can still break it up like this. Let's see, we have 2 times 2 times 2 times 3 times 3. We're still just breaking it up by multiply, just kind of a different strategy. So here I can write it like this. So I've broken this up. Now remember what I'm looking for in square roots. Remember with square roots, you're looking for something squared, or something twice, multiplied twice to be specific. So if you keep that in mind, here's a trick that can help you to solve these easily if you were having trouble just breaking them into the biggest pieces, like we did a second ago. Notice I have this 2 twice. That's nice. I can pull it out. Let's see, that's left over, so I'll keep that under. That 3 twice, so I'll pull it out, attaching by multiply. So what I get, let's see, I pulled out the repeating stuff since that's what square roots are looking for. To get the 2 and the 3, 2 times 3 is 6. This right here had to stay up under the bar because it was not a pair. It was not part of a pair. It was by itself, and again we were looking for stuff that happened twice. So I have 6 square root of 2. Which is exactly what we got a second ago. Let's see if I can put that on here somehow. Maybe not so easily. But you have two options. A moment ago we saw you can split it into a square root, something that you know is a perfect square, still attaching by multiply. Go ahead and take that square to get your 6. Then you have your 2 left. Get that answer. Or just now what we saw is that you can break it up into all of its smallest pieces, its primes, and when you find pairs, sets of 2, take those out from under the bar. Yeah, so for 2 2's, you just take 1 out. That means you took the square root of it. You have 2 3's, just take 1 3 out. And then you have that 2 left up under there. Both methods work, and I have no preference to which one you use. Something you should note. When we are dealing with square roots, like we had the whole square root of 25, right? which asked what times what equals 25, right? And we said 5 times 5. So 5 was the answer. Notice something for me. What if I had asked the square root of negative 25? Is it possible to get something times itself equal to a negative number? Let's see, negative. Well, we know 5 times 5 is 25. Negative 5 times negative 5. No, that's still 25 because they have the same signs. And you can't mix them because it has to be the same number. That you can't write negative 5 with positive 5 because it has to be the same number being repeated. That's the rule that you follow. This right here is not okay. Not okay. In fact, the answer is no real solution. Later on in math, you'll play more with this kind of number because it does come up. But the idea is that negative is not allowed. Mathematicians have found a way to rig it and let you keep working with the numbers. But as far as we are concerned, the fact that it's not a real number is enough to make us stop. If you ever see a negative up under the square root, no real solution. There's nothing you can do. That being said, though, also, by the way, note, the product rule breaks here. If you have a negative there, step away. Don't even try splitting it by multiply or anything like that. It's not going to work out for you. Up under that bar, if you have a negative, you cannot do the problem. But you can do problems where you have a negative in front. So let's look at one more example to make sure that we're not getting too confused with this. Negative 5 times square root of 32. Or most people would just say negative 5 square root of 32. However you like to see it. To simplify this, you have a couple of ways. I know that 16 goes into that, and that's a perfect square, so I'm going to split it into its perfect squares by saying, you know what, that's the same thing as negative 5 square root of 16 times 2. You can do the other method if you want, I don't care. But the negative was in front of that 5. It wasn't up under the bar, so it gave me no problems at all. So I'm going to keep it there. Negative 5 square root of 16 square root of 2. That gives me a 4. Negative 5 times 4 is a negative 20 square root of 2. So yes, you may have negatives in front of your stuff. Even in front of your square root. You could have had negative square root of 25. That would have been okay. Just not under the bar. Not like this, but you may have it in front. And remember, it's just attached by multiply. So if it's in front, it's timesing it by essentially a negative 1. So here you would get your 5, and you would have negative 5. Because you did this operation first, which was okay to do. It had no negative under it. And then you brought the negative on down or over in front of it. Okay, practice these things and let me know if you need more help. So let's look in our